Hey guys, welcome back. Today we're going to learn about dielectric strength and all the stuff that you do with it. So let's start with the term dielectric strength. It can actually be used a couple different ways in the problems that you're going to have in the text. All right, but always what they mean when they say dielectric strength is the maximum electric field. Okay, anytime a capacitor, say, has a particular maximum voltage or maximum charge or whatever it may happen to be, it's always because of the dielectric strength and the limit that that places on what the electric field is allowed to be between the plates. Okay, so anytime you've actually seen a spark, any kind of a spark, right? That spark represents what's called dielectric breakdown. Okay, so if we're talking about, let me write that phrase, dielectric breakdown, what that's going to relate to is basically lightning on whatever kind of a scale you might happen to have. Dielectric breakdown is where the electric field that is present at a surface is momentarily greater than the maximum electric field, and the result is sparks. Sparks, it doesn't sound that, well, it depends exactly like where the sparks are happening and how big they are and all that kind of a thing. Sparks can actually be, say, incredibly bad, all right? So what I'm going to do right quick is have you witness some dielectric breakdown on a very small scale. I hope this comes out over the video. I don't know how visible it's going to be. I've tried before to film sparks, and it doesn't work that well. But you'll be able to hear them, even if you can't see them especially well. So, you know, depending on the size of the sparks and where they are, it might not be a big deal. And in this case, it's not really going to be that big of a deal. All right, so let's see. Can we see in between the plates? Can the webcam do that? Oh, yeah, I'm seeing a few anyway on my end. All right, so if you see any flashes of light, that's what those are, is some dielectric breakdown that's occurring. All right, and you can definitely hear every single one of those. So dielectric breakdown, right, that's where you have charge jumping from one plate to another. Okay, that's what sparks are. So if you've ever had a cotton sheet next to a fleece blanket and you rip them apart really fast and there's like a 3-inch long spark, or you stand up off the fuzzy couch and then you touch someone and bazap, right? Or the faucet or whatever thing you happen to touch next, right? That spark is dielectric breakdown occurring. It's a stream of electrons that are jumping from one object to another, depending on which one has the positive or negative charge, right? But always it happens as a result of the electric field at the surface of the object being momentarily greater than the dielectric strength of the surrounding medium. All right, so let's think back through some of those scenarios. The dielectric in all of those particular ones that I mentioned that are familiar to you, like zapping somebody who stand up off the couch, or the spark that you get between the cotton and the fleece blanket, or even lightning for that matter. For all of those, the dielectric is air. And so in each one of those cases, the dielectric strength, the maximum electric field, is a number that is 3 times 10 to the 6th. 3 times 10 to the 6th. All right, now, where could I find that number? Am I supposed to just know that? No, you're not supposed to just know that number. There's only one number in this whole unit that I expect you to have memorized, and that's actually the dielectric constant for air. The dielectric constant for air is 1. All right, but the dielectric constant, kappa, is not the dielectric strength. They are, however, both in the same table in your textbook, right? At least for honors. So that would be, again, the table on page 791. So if I look, the very top thing there is air, Dielectric constant is basically 1. And then it says the dielectric strength is, all right, now if you're not on page 791, you might want to get there and just look at it so you're seeing the same thing as me. It says 3. Well, I wrote 3 times 10 to the 6th, so if you look at the column heading, it says right there, dielectric strength in 10 to the 6th volts per meter. So it's in millions of volts per meter. All right, we'll come back to that unit because that's not the unit that you were maybe expecting since I said it was an electric field. Okay? Electric fields are usually measured, or at least were measured in the last unit, in newtons per coulomb. But I'm saying that that's an electric field. So a volt per meter is somehow also a newton per coulomb. Okay, so we'll get back to that. But in all of those cases, whether it's lightning or spark jumping off your finger, it's happening because the electric field, say at the surface of your finger or between a cloud and the ground, the dielectric, the electric field was momentarily greater than the dielectric strength, and the result is dielectric breakdown, sparks of whatever scale, until the electric field goes back down to this maximum allowed value. So charge will just keep jumping from one plate to the other, plate being a term loosely used in all those familiar examples, until the electric field gets back down to this allowed value. Okay, now, let's talk about that unit volts per meter, and then we'll talk about what this has to do with capacitors. Okay, so the reason a volt per meter is the same thing as a newton per coulomb actually has to do with this equation right here. Let me move this over here. All right. In this equation, we already said that the E stands for electric field. So if you solve that equation for electric field, you get delta V over D. Well, delta V is measured in volts, and plate separation is measured in meters. Okay, so an electric field is measured in volts per meter or newtons per coulomb. Now, what does that unit really mean? Like if I say it's 3 million volts per meter, right? What exactly is that all about? Okay, so if it's 3 million volts per meter, just to help you understand, if I put my hands a meter apart, whatever, I can't do this in the video so that my hands look normal. There, okay, let's say that right there is a meter. It's not, but that's okay. If this is a meter, if the dielectric strength of air is 3 million volts per meter, then it would take a potential difference of 3 million volts between my two hands in order to get a spark that is a meter long. All right, so for the capacitor that I held up earlier in the video, those plates are only a millimeter apart, right? So using my equation delta V equals ED, if the electric field can be a maximum of 3 million volts per meter, and the plate separation is 1 millimeter, which would be 0.001 meters, right? 1/1000th of a meter. That would mean that the potential difference on the plates was 3,000 volts. And that's exactly what the power supply that I had them hooked up to supplied, was 3,000 volts. And that's the most it can actually supply, okay? And if I have the plate separation set any larger than 1 millimeter, like say 2 millimeters, it can't do it. It can't make those sparks. I won't get dielectric breakdown because that would take 6,000 volts. Okay, so can't do it. All right, now if I expand this to the larger scale of a lightning bolt, just as a gross approximation, if the distance between a cloud and the ground is a kilometer, that's 1,000 meters. If this number is 1,000, that's 3 billion volts is many volts. Don't get struck by lightning. It's usually a bad idea. I mean, you know, if you have the choice, all right? So yeah, 3 billion volts between sky and ground based on the dielectric strength of air. Okay. Now, there are various factors that can change the dielectric strength for a particular medium, okay, such as if there are water droplets. So lightning happens much more easily if there are suspended water droplets in the air, also known as rain. Okay, but regardless, right, if we just pretend that is the electric field, then there you are, 3 billion volts. All right, now, the dielectric strength of air is 3 million volts per meter. Other materials have a different dielectric strength. So if I look up in my table here, say paper, and paper is 16 million volts per meter, because remember that's how that table is scaled. So it's a lot more difficult to break down paper because instead of just being 3 times 10 to the 6th, it's 16 times 10 to the 6th. So it takes 5 1/3 times as many volts to break down a meter of air. Okay, so that means that if I repeated that same experiment with the parallel plate capacitor, but I put one of your note packets in between the plates. Okay, maybe that also changes the plate separation, but even if I didn't change the plate separation, with the paper in there, we do not get dielectric breakdown because the dielectric strength of air is greater. All right, so let's talk about what this would look like in an actual problem. Okay, like what would I ask you to do? So a typical thing is going to be, all right, tell me what is the maximum voltage I can put on a particular capacitor, or spin it the other way around. We could ask for, say, the maximum charge I could place on it, given, say, like the plate separation or something, okay? So the reason this particular capacitor says 5.5 volts maximum is based on this dielectric strength idea. There's always a maximum potential, charge, whatever it is, based on the maximum electric field. So somewhere you should write down that word maximum and say equals breakdown or something like that. If they in any way imply that you're finding the maximum voltage or the breakdown potential or anything that hints at those two ideas, then you are going to plug in the dielectric strength for the electric field. That's the key idea that a lot of people miss when they're doing these problems, is they don't understand what to do with the dielectric strength or where to begin, because a lot of the time it will look like, I don't have enough numbers. What do I do? What you do is, if they say the word maximum, you look up the dielectric strength and you plug that in for E, the electric field. That's what you do. All right, so let me make up an example problem. Oh, there you are. Look, I wrote a problem on the board. So it says we have a mysterious 15 microfarad capacitor. If the capacitor says do not exceed 6 volts, step 1 is we're going to determine the charge at this voltage. All right, now remember, part of the problem for any capacitor question is you have to know what the letters stand for. So we are trying to solve for Q. That's charge. All right. And then in part B, it says if the dielectric is strontium titanate, kappa is 233, the dielectric strength is 8 times 10 to the 6th, determine the plate area and the plate separation. All right, so we're trying to find A and D. All right, see what you can set up. I'm going to pause the video, and then I'll resume, and you'll be able to see the correct work. There's our answer for part A, and pause to do part B. And there you can see is the work for the last part. Don't be alarmed if you get what seem like outrageous values, such as huge surface areas or really small plate separations. That really can actually happen with capacitors. Okay, hope that helps.